Welcome to Us, Fall Asleep as a Service. Today we're going to continue talking about hybrid cloud security. This is section 2. It's called Hardening the Cloud Environment. I'm going to fill you in on some of the controls you can use to secure the cloud environment. I will tell you the value of using more micro-segmentation to protect the cloud network and introduce some of the security challenges around implementing containerization. Many of the security controls that are used to protect traditional data center architectures have equal value in a cloud-based environment. After all, behind every great cloud, there's a great data center. Organizations need to incorporate cloud security into a more general organizational security program and ensure that all requirements are covered equally. In fact, security is typically listed alongside governance, business, and management as one of the 4 main functional areas that span both traditional and cloud-oriented IT functions. A number of technology areas within a cloud functional reference architecture can be complemented by the cloud security program. The most important ones are shaping security standards, shared responsibility, defense in depth, monitor, detect, and respond, continuous regulatory compliance, secure applications, data-centric security, dynamic infrastructure hardening, shared access management. These are some of the technical cloud security principles and capabilities. Let's start by recognizing the challenges with traditional infrastructure security. In a traditional pre-virtualization data center, infrastructure security was about using a hardware firewall, intrusion detection system, IDS, and intrusion prevention system, IPS, to separate servers into individual network segments and apply security controls to the traffic passing between those segments. Security within the segments themselves was enforced on individual servers by keeping security patches up to date and implementing host-based IPS and anti-malware solutions. In the virtualized or cloud data center, you cannot rely on hardware appliances to provide the network segmentation because, more often than not, the traffic travels from east to west, from virtual machine to virtual machine, and it never meets the controls on the physical network. Plus, in a dynamic cloud environment with rapid provisioning and deprovisioning of compute instances, traditional patch management approaches just don't scale. So how do you provide security for compute instances? In a cloud environment, and especially where different customers may be sharing the same physical infrastructure below the virtual compute instances, you need to be able to provision virtual compute instances securely. This includes, but is not limited to, the following: virtual machine hardening, authentication and authorization, host-based anti-malware, secure communications, secure backup and recovery, VM security scanning, remediation, compliance monitoring, secure deprovisioning, and secure multi-tenancy. Most of these controls are dealt with by organizational policy. There isn't much difference between how some of these issues are dealt with in a traditional data center and the way they're dealt with in the cloud. However, secure multi-tenancy is tied very closely to the cloud infrastructure, so it's worth looking at it in a little more detail. Making sense of network multi-tenancy. According to the Gartner IT Glossary, multi-tenancy is a reference to the mode of operation of software where multiple independent instances of one or multiple applications operate in a shared environment. The instances are logically isolated, but physically integrated. In a cloud-specific networking environment, multi-tenancy allows different tenants to share the same physical infrastructure and, if implemented correctly, even the same private IP ranges as one another without running into any resource or communication issues. Let's understand software network overlays. SDN is starting to become popular in both on-prem and cloud-based data centers because of the flexibility it can provide over a traditional data center network, which is often referred to as a hardware-defined network. For years, enterprises have built networks around hardware switches and routers, and it's been accepted that the network is defined by the capabilities offered in the network operating system. Because Ethernet follows standards for the most part, there is interoperability between network devices from different vendors, and devices talk happily to one another. However, some of the advanced features remain specific to individual hardware vendors. One example of this has to do with virtualizing individual network devices into a single distributed device. HPE chose to develop and use the IRF protocol, whereas Cisco went with VSS. At a high level, both protocols offer similar functionality, but to implement the technology network-wide would require standardization on a single hardware vendor. Alternatively, software network overlays allows network administrators to manage the network at a software abstraction layer. SDN-compatible switches, often supporting the open flow protocol, separate the control plane from the data plane, allowing an SDN controller to programmatically control the switch using a northbound API. This effectively removes the barrier of using a single hardware vendor while still maintaining a network fabric with a high level of functionality. The concept of SDN also extends to a virtualized network. For example, in a cloud, and allows the virtual switches to be programmed independently from the hardware network underlay by cloud automation tooling. This provides a lot of flexibility from a security perspective. Here are 3 main features of an SDN overlay in a virtualized environment. Micro-segmentation. Traditional networking separates logical networks through virtual local area networks, VLANs, Internet Protocol, IP subnets, and routers. But more and more traffic in a cloud or virtualized data center is going east-west rather than north-south. This means that security devices that have been deployed to offer parameter protection are no longer able to see as much of the network traffic as they previously could. Microsegmentation deals with this by deploying distributed routers at the hypervisor level and enabling access, control lists, ACLs, at the closest enforcement point to the VM itself. Between the virtual switch and the virtual network interface controller, that's the NIC. Service chaining. Service chaining, also called service composer or service insertion, is the ability to integrate other network security or network management devices into the cloud network environment. It provides particular value for east-west traffic. For example, both NSX and DCN can integrate with third-party next-generation firewall solutions, like the physical and virtual firewall solutions from vendors such as Fortinet or Palo Alto Networks, to add an additional layer of control for the traffic that is passed in between VMs. The security chaining configuration is typically managed at the distributed router level to provide the needed flexibility. Secure access. Network overlay solutions support the ability to create VPN tunnels for use to provide either secure access to clients or secure site-to-site tunnels. But all network virtualization platforms offer integrated management capabilities, but the best practice would be to use a cloud management platform such as VMware, vRealize, to automate the creation of network instances. Let's consider the value of containerization. Recently, a new method of provisioning virtualized compute has started to become popular. This is driven by emerging vendors such as Docker and Mesosphere. Standard virtualization offered by VMware or Microsoft Hyper-V or KVM provides a hypervisor upon which multiple instances of an operating system may be provisioned and used. Containerization differs from this by offering OS-level virtualization, multiple isolated user space instances sharing a single kernel. This approach provides a lightweight virtualization technology and affords much better use of system resources. A container has its own process space, network interfaces, root file system, and set of binaries and libraries, both static and dynamic. Containers on the same OS instance share the same running kernel. You no longer need to build a dedicated OS instance to support a single business application. Instead, the application can be containerized and run in tandem with many other container instances on top of a single OS instance. But please note, there are a lot of advantages to using container-based virtualization, but there are also a lot of security concerns that need to be addressed in order to have a secure running container environment. In particular, it's worth noting that containers running on top of a single kernel create a single point of failure. If a malicious or misconfigured container somehow managed to cause a kernel panic in the host OS, all containers would be impacted. A full study of the security of containers is beyond the scope of this, but here are some tips worth considering. 1. Apply security patches to the host OS regularly. Better still, use a security-hardened host OS. 2. Make sure patches are applied not only to the running containers, but also to container images. Container instances typically have a short operational lifespan. 3. Only deploy containers from trusted sources. 4. Run containers with limited privileges. 5. Apply appropriate limits to avoid resource exhaustion. Finally, make sure you restrict networking ports to only those that are needed. Thank you for joining me tonight. Next time, we're going to talk about securing the application lifecycle.